So consider this. You may know you shine some white light through a prism, and you find that it is broken into different colors. I don't have all the colors available readily here, but get the idea. It becomes a rainbow. Um, what else? Green, maybe. Okay, and so we're observing that this white light contains these different colors, and the thing that's different about these is that they have different wavelengths. Um, and I suppose that presupposes that you appreciate that light can be considered as a wave. In fact, it's all part of um, what we call the electromagnetic spectrum. And it's just that the visible light is a small range of it that our eyes are able to detect. So the whole spectrum covers a wide range of different wavelengths. And quickly, electromagnetic radiation can be thought of as having um, two components, electric and a magnetic component of the wave. It's not really particularly relevant for, oops, I was going to do that in white, for this discussion, okay? But what's really important is that you appreciate that there's the two components and they're 90 degrees from each other. But anyway, there's a wavelength. There's a length to this oscillation, okay? And that's what we're going to focus on here. And so, in fact, if you look at this whole electromagnetic spectrum, that is all the different wavelengths that are possible, you'll see that there's a lot of familiar radiation in there. So, you could go from, let's cover some wavelengths here, kind of at the atomic level. So maybe 10 to the minus 11 meters. Okay, roughly that scale, like tiny, tiny little short wavelengths. Or what about if you go to, really long wavelengths, kilometer scale on the other end? And you'd find that, in fact, visible light, well, visible light just falls in somewhere in that range. And in fact, visible light specifically spans from red at about 700 nanometers, so 700 times 10 to the minus 9 meters in wavelength, to blue light that's around 400 nanometers. Okay, 400 nanometers, 10 to the minus 9 meters, right? And that's just a tiny little range of this whole spectrum. To show you what I mean by this range, well, blue, actually, in fact, the end of the rainbow is violet, right? Violet. Well, what if you go a little bit shorter wavelength than that? You might get to ultraviolet. And in fact, this little discussion enables us to potentially, if you've heard about ultraviolet radiation, UV, you may know you can protect yourself from it. There's quite a bit of energy in that radiation, and it can damage the tissues of your skin. It can give you sunburn or skin cancer. So there's more energy associated with the energy that's coming on, that's being transmitted in this light. You go a little bit more shorter wavelength and get into X-rays. What about on the other end? Red. What about a little bit past red? How about infrared? A little bit longer wavelength than red light, and so on. And you can get radio waves and things in here. So there's my point here is there's a whole spectrum, and what we can detect with our eyes is just a tiny little portion of that. Sometimes, so I spoke about the energy that's contained in this radiation. And in fact, energy is quantized, that it's transmitted in these little packets, little small amounts. Sometimes we call them photons. And so you can actually calculate that photon energy with an equation, which some of you may be familiar with. It's E equals hc over lambda, where lambda is the wavelength. Okay, and so that's a little equation, and h is the Planck's constant, c is the speed of light, and as I said, lambda, well, that's a pretty bad looking lambda, isn't it? Let's fix that lambda up. For some reason, of all the Greek letters, I have most trouble with lambda. Anyway, that's the wavelength there. Okay, wavelength. I'll give you an example of this in a moment. So that tell you the amount of energy, and you could calculate the amount of energy in joules, or in fact, I'll show you another quantity that's quite useful sometimes. So let's actually look at this. Let's look at the visible spectrum. Okay, let's look at the visible spectrum. And so we know the visible spectrum, just as a interesting little quick calculation to give you some values. Visible light spans from 400 to 700 nanometers. Okay, and what type of energy does that involve? So we'd have to calculate E equals hc over lambda, where h is the Planck's constant, as I said, and that has a value of 6.63 times 10 to the minus 34 joule seconds, and c has a value of 3 times 10 to the 8 meters per second. But when we're dealing with things like with electrons, it's and with energy at this level, it actually, sometimes the joule isn't the most practical thing to use if you want to get numbers that you can kind of roll off the tongue, if you will, that are easy for our human brains to remember. So what we can actually do is we could take a value in joules, like the Planck constant there, 6.63 times 10 to the minus 34, and do a little conversion to it. So we say that's in joule seconds. Well, what if we divided that by the charge on an electron? Okay, so that's 1.602 times 10 to the minus 19 units of charge. That's a coulomb. Okay, and that's the charge on an electron. What if we if we take an electron and accelerate it through a volt? Well, a joule per coulomb is just a volt. So in fact, joule per coulomb, that cancels out, and we could define this charge on an electron accelerated through 1 volt. That is, you get 1 volt like this, and we're accelerating an electron across that 1 volt. Well, we could go ahead and define that charge times that voltage, 1 volt, as an electron volt. And then we find that we get a value that's a little bit more useful often. And I'll show you that again with the visible spectrum. So that works out to 4.135 times 10 to the minus 15 electron volt seconds for the Planck constant. So now what we can do is we can say, all right, let's take this 400, 700 nanometers, calculate the photon energy, and if we do that, we'll find that the photon energy for, say, blue light, okay, is going to be 4.135 times 10 to the minus 15 electron volt seconds divided by, and multiplied here by 3 times 10 to the 8 meters per second, and then divided by the wavelength. And we said, well, the wavelength of blue light was 400 nanometers, so 400 times 10 to the minus 9 meters. And let's see what happens. Meter cancel out, seconds cancel out, and we end up with electron volts. And we find that blue light has a photon energy of about 2.8 electron volts. And similarly, if we did that for red light, go through the same exercise, we'd find that red light is around 1.9 electron volts. And in fact, you can actually get a little bit of visible spectrum. You can see into violet, a little bit higher energy than this. So a nice little result that you may want to remember is that visible light in these useful units of electron volts spans about 2 to 3 electron volts. So when you consider say optical transparency and what this visible light is doing to a material, does it have enough energy to excite an electron, for example, it's useful to bear in mind that visible light has photon energies from 2 to 3 electron volts. All right, thank you.